announcements made. Okay, we are recording, so let me get the announcement. Let's go from current slide, and we'll actually back up. Okay, that's where we'll begin today. Okay, first, have you done student course evaluations? Okay, but you know about them, right? You know how to do them, right? Where to go, right? Okay, please get them done. You don't have to do them until, got to get them done by August the 8th. Don't wait until August the 8th, okay? Get them done at some point sooner before the term gets over. You can wait and see what that final grade is if you want to. It'll be in well before August the 8th, knock on wood. Okay. All right, good to hear it, thank you. Okay. Now, the other announcement deals more with my office hours. I may have made this one before, but just in case you weren't here to hear it or whatever, I'll record it again. My Mondays and Wednesday office hours haven't changed. I only have 8 to 8:30 in the morning and 5:30 to 6 in the evening, or at the end of this class at 5:25 until 6. That's all I got on Monday and Wednesday. But Tuesday and Thursday, I had listed that I'm free from 10:45 in the morning until around 4:30 in the afternoon when I have to go to the Birmingham East Campus to teach a class there. However, as it turned out, the last several Tuesdays and Thursdays, and it's in just about every one, and will continue for tomorrow and next Tuesday. After that, I think I go back to the regular things. I'm going to have to go to the Birmingham campus earlier than for leaving here at 4:30. For instance, tomorrow I've got a meeting at 2:30, so I'm going to have to leave here by 2 o'clock. So that's been it's happened several times, not always, but several times. Then on Tuesday, I've got a hearing that is supposed to start at 1:30, so I have to leave here by 1 o'clock. So my office hours on this campus tomorrow are 10:45 until 2, approximately 2, and then on Tuesday it'll be 10:45 until 1, probably a little before 1, but something like that. Then I have additional office hours over on the Birmingham campus, but I can't tell you exactly where I'll be. More than likely, Birmingham East Campus in the nursing building in room 214. But I can't tell you when I'll be there because I have meetings that I don't know how long they're going to go. But later in the day, close to 5 o'clock, I'll be up there. Before 5, though, hopefully. Yesterday I was a little after 5, but that was unusual. Okay, any questions on anything we've done up till now? All right. Please, folks, get your research papers in. I'm going to get that one done while I'm thinking of it, too. Some of you have, some of you haven't, so please get the research papers in. You only have, 2 weekends left, I believe? That's all, if that's when you work on things like that. All right, example 3. They're not on the slide set, so let's do it using, yes. I have it mostly marked, but I haven't figured up the score because I had to use part from one test and part from another test, and I think I've got yours totally marked, but I just haven't figured out the score yet. But it's been that way for a while, and until we get this hearing over on Tuesday, it may not change. Well, I take that back. Friday, I have an infusion scheduled, and that's usually, you might think it's a bad thing, it's sometimes a good thing, because I have to get there an hour ahead for blood work, and then I have close to an hour to kill, and that's when I get a lot of good grading done. So maybe I'll get it graded Friday, okay? I don't know for sure, but maybe I will. Now, even after they start the infusion, I can grade for a while. But before they start the infusion, they give me Benadryl in the infusion. And once I take the Benadryl, I've got only about 15 or 20 minutes before I'm out. You know, it just knocks me for a loop. So, what's that?
They have allergies if you're out cold.
Yeah. Yeah. So I, knock on wood, don't have that many allergies, so I don't usually take Benadryl. So when I do, and they give it to me, and they give me 2. When I take it at home, 1. They give me 2 with 2 Tylenol, which whenever I take Tylenol is 1. So they give me double on both, well, normal dosage, but it knocks me for a loop. All right, example 3. Find the volume of the solid region bounded by the paraboloid z is equal to 4 minus x squared minus 2y squared. Okay? And the xy plane as shown in the figure. We don't have the figure, but I'll give you approximately what that becomes. Now, I think even in the figure, they messed it up a little bit. I'm looking at it to see. No, I think it may be okay. But anyway. Well, I'll just give a quick, well, what I'll do, I'll try to give a little bit of a description of it. Here's the x, y, and z, 1, 2, 3, 4. It goes up to 4, out here on x to 2, and on y they go, say to 1.5. That's the part I don't quite, I'm not sure that's quite the scale. And it's going back this way, 1, 2, and out this way, 1.5. Okay, so as a base it's here, and then it goes up to there. So that's sort of your paraboloid. Pretty ugly looking, but hopefully it'll give us everything we need. Okay. Now, this base in the xy plane, and that's where it begins, this base down here is an ellipse. And that ellipse is make z equal 0, and you have x squared plus 2y squared is equal to 4. Divide everything by 4. And you have x squared over 2 squared plus, yeah, they're right, y squared over root 2 squared. So their picture is right. It's not 1.5, but, oh, I didn't draw it right, did I? It goes here, 1.5. I messed it up on this one. 1.5 here. Okay, so let me take that one out of there. It's not quite 1.5, it's 1.4. Okay, let me take that one out too. Okay, sort of like that. Okay, now is equal to 1. That's the ellipse when z is equal to 0. All right, here's Davis. Hold my pen. Okay, bottom part of the alphabet's holding in strong. Ricky's having to hold up the whole top part of the alphabet by herself. Okay. So, there is your ellipse at the base of this thing. What we're trying to do is find the volume of that ellipse paraboloid. Okay. Now, technically what we do here, we can, once you set that up that way, what you're going to do is a dx and a dy, and you're going to go from there. So you have to figure which one's going to work best with the other, better than the other. And this is sort of, okay. You kind of pick, and I would say the last integration needs to be your dx. So, because that goes from minus 2 to 2, okay? The other one's going from minus root 2 over root 2, so we don't want to do that. I mean, you could, it's not bad, but it's just a little awkward. So let's do, the last integration is going to be the dx integration, okay? So the last integration is going to be the dx's as we go here. So the first integration is going to be dy's here, okay, as you go up and down. So you need to get this portion of the ellipse and the corresponding portions to it as a function of x, because your last integration is going to be dx. So ultimately the dx is going to be at the end, because that's going to go from, now we have another issue here, and let me go on and cover that. This is symmetric about the x-axis and the y-axis, okay? Z does it, but we're not worrying about that, okay? So if we just do in the first quadrant and multiply it by 4, we're going to have it not. So rather than going minus 2 to 2 on x, let's go 0 to 2 on x and multiply by 4, okay? So we'll have 0 to 2 on x, and we'll multiply the whole thing by 4, because you got something in this quadrant, that quadrant, that quadrant, that quadrant, and they're all the same. So we're just going to do this. So there is going to be that. Now, you need to express this y as a function of x. So if I draw sort of that thing, now this is a circle, so it makes it a little harder to come up with this, but because we know that in the xy plane, if we, let's see, I think I'll go back to this form, x squared plus 2y squared is equal to 4. Okay, let's turn that around and solve for y. So that would be, first thing, let's first subtract x squared from both sides. So that gives me 2y squared is equal to 4 minus x squared, and then divide everything by 2. Okay, so in y, and then take a square root. So y is equal to, and because I'm staying in the first quadrant, it's just going to be positive, so we don't have to do minus. So it will be the square root of 4 minus x squared over 2. So you're going in y from 0 to the square root of 4 minus x squared over 2. Okay? And then your function here, the z, 4 minus x squared minus 2y squared, that's your z value. Okay? And I didn't leave enough room. You're doing first your dy's, and then you're doing your dx's. Okay? And the dx is going from 0 to 2 because we're staying in the first quadrant. Okay? Now, all right, here's Rachel. Out to be a pretty good class, well, so far. Still not big, but okay. Glad y'all are here. And so let's do the integration now. 4. We're not going to mess with the x's yet, so that goes 0 to 2. let's mess with the y's, okay? So what's the antiderivative? Now we're taking the integral with respect to y. Antiderivative of 40y is 4y. Say that again. Yeah, antiderivative of this expression in the middle with respect to y. Okay, not quite yet. The x is counted as a constant, so that's going to be minus x squared y, just like the 4 was a constant. Okay? All right, you do it with respect to that. And then what you were just starting to say was 2y cubed over 3. Perfect. And we're going to evaluate that from 0 to, now remember, this is y values. Y equal the square root of 4 minus x squared over 2. Okay? Now, and then we're going to do our dx later after we do that one. So it'd be 4 times the integral from 0 to 2. Now let's plug in the y. That would be 4 times the square root of 4 minus x squared over 2. That's all under the square root, minus x squared times the square root of 4 minus x squared over 2. Okay, minus, now we're going to, got a 2/3 in front, and we're going to cube that thing there. So basically that's going to be, I'm going to write it in this form, 4 minus x squared over 3 cubed. Okay? It's kind of a mess, isn't it? dx. Okay. See if they've done anything here to make it a little more palatable. Okay, number one, they're doing the whole thing, and I'm just doing a quarter of it, so that puts my 4 out there. Now, here's a little trick that they did do. Now, is it all right for me to erase my drawings and stuff? Because I don't have enough room to work. So I'm going to come up here and erase all this. Hopefully you got it if you needed it. Okay. And I'll probably erase this too, even though I don't think I'll need it again. I think we've used that for everything we needed. Okay. I'm going to have to erase more, but I'm going to do it piecemeal. Okay. The thing that they noted, which is a good idea, is rather than doing this, this is a, in fact, I'm going to come down here and whoa, hit the wrong key. I'm going to correct down here, okay? Notice this is the same for both of those, and you got a 4 minus x squared, and even up here, and which was a good move on their part. This is a 4 minus x squared times y. They just treated that as one term, and that was times y, and then you plug in the y for that, and you get that. Oops, no, I didn't erase this part. Okay. And this gives you, no. Yuck. All right. 4 minus x squared times the y is the square root of 4 minus x squared over 2. Okay, minus that. Now, the thing to note here is that 4 minus x squared here is 4 minus x squared to the 2 halves, right? That's to the 1 power, which is 2 halves. And this is to the 1 half power. So this is 4 minus x squared to the 3 halves over the square root of 2. And this is 4 minus x squared. I think I left off my half here. Yeah, I was supposed to plug this in. I left off my radical here. Sorry about that. Okay, that was supposed to have a radical there. That raised to the 3rd power. Well, the thing is that this part, and that is a 2 down there, not a 3. I don't know where my brain is here. We're plugging in y is equal to that, and that would give it to us, okay? So this is the square root of 4 minus x squared cubed over 2, and this is the square root of 4 squared cubed over 2. Now, actually this is over 8 because you're cubing that, but this is just over the 2. Because this part doesn't have a 2 in the denominator. I think it's supposed to anyway. Okay. So basically what you have then is this. All right, let's just check and make sure. 4 minus x squared times y minus 2/3, and that's evaluated there. And that would be, they skipped just a ton and a half of steps here. I'm going to have to plug those in, okay? So I'm going from this line up to here. I think I'll go all the way to the top. This will be 4 times the integral from 0 to 2 of 4 minus x squared to the 3 halves power over the square root of 2, because, yeah, that's right, minus 2 over 3 times the square root of 2 times, I shouldn't do that, hold off, I mean, not do that yet. I'll probably do it in the future, but not yet. Okay, minus 2 over 3 times the square root of 4 minus x squared. Didn't mean to put the radical. To the 3 halves power. And this time it's over 2 times root 2. And this 2 and that 2 are going to go away. So that's going to help a little bit, I think. Okay? Now, and this will be dx. All right. I think I see where theirs is coming from now. So if you think of this, this is this expression right here, minus 1/3 of that expression right there. So that gives you a total of 2/3 of this expression right here. Okay? So what we'll have now to rewrite this is 4 times 2/3, that would be 8/3. and I write 83. I don't know what's wrong with the brain, okay? 8/3, and we'll also pull out the root 2 in the denominator, and that'll give us the integral from 0 to 2 of 4 minus x squared to the 3/2 power dx. Okay? Now, quick rehash on how that happened. This down here was 4 minus x squared to the 2/3, 2/2 times this to the 1/2, that's to the 3/2 over root 2, because that was in the denominator. This one over here was minus 2/3 of this whole thing to the 3/2 power. And that would be this thing to the 3/2 power, and this 2 would then be 2 times 2 times 2 in the radical. Pull out the 4, the square root of 4 is 2, that canceled out the 2 here, by the way, wherever it was, right here, canceled out those and left your root 2 down there. So now you have this whole thing minus 1/3 of the whole thing. That gave you 2/3 of the whole thing. So the 2/3 comes out. 2 times 4 is 8 and the third, and the square root of 2 came out. So that leaves you that to the 3/2 power. Now, that's not a particularly easy integral to do, except for the fact that it's a trig substitution. And the trig substitution like that would be this one. Let x equal 2 sine theta. Then dx is equal to 2 cosine theta, d theta. Okay? Also, x squared is equal to 4 sine squared theta. When you negate that, that gives you a minus 4 sine squared theta. And then if you put a 4 in front of that, that would be this thing right here. So 4 minus x squared is equal to 4 times 1 minus sine squared theta, d theta. Okay? I forgot my d theta. No, I'm sorry. No d theta there. We're not doing d's yet. That was over here. Okay? Well, this is cosine squared theta. So this is, running out of room, 4 times cosine squared theta. Okay? Now, backing up from there, this is not the same problem. Okay. Now we want to do the square root of that. Actually, the 3/2 power of it. But let's do the square root first. The square root of that would equal to cosine theta. Okay? But then we need to cube that, and that gives us the integral. Okay, we've got to change our limits. But it's 8 over 3 root 2 times 8 cosine cubed theta. Okay? Because you're cubing this thing in here, and the thing in there with the square root was 2 cosine theta. Okay, so that's 8 cosine squared theta d theta. 8 cosine squared theta. That's this part. Your dx, remember, was another 2. So that makes 16 cosine theta d theta. Cosine theta d theta. Well, now you got a cosine to the 4th, which is exactly what they've got. And let me oh man. Let me erase some more here so we can continue. Okay. These take so long to do, but really, step by step, they're not bad. They've just got lots and lots of steps. I can't get my thing to erase here. Okay, so what we've got now is this thing right here has turned out being that thing. Okay. Now we now got an 18 in front, and 8, I'm not sure that's 18 now. Is that 16? 16. 16. 16 times 8 is 48. That's 128. All right. So that's going to be 128 over 3 root 2. All right. Times the integral of cosine 4th theta d theta. Now I never changed my units. Let me go back and change those. In x's they were 0 and 2. Okay, when 2 sine x equals 0, theta must be 0. So the 0 stays the same. And for 2 sine x to be 2, that means theta has to be pi halves. So our upper limit here, I don't need that. Can't get my pen to work. Okay, there we go. 0 to pi halves. All right, now, they do something very, very sneaky here. And I can't even begin to tell you where to go back and find it, but I'm going to look, because I'm sure it's in here. Page 534, way back. That sounds like Cal 2, maybe even Cal 1. $534. One more. What is that? That's Cal 2. Okay. Now, here is Wallace's formula. And I don't remember this one, memorize it, but you should recognize it. Okay? It has those limits, 0 to pi halves, and if n is even, and that is 4 is even, then Wallace's formula says this will be, excuse me, okay, I'm going to bring down the thing in front, 128 over 3 root 2, if it'll write, times, okay, 1/2 times 3/4 times pi halves. Okay, that's Wallace's formula. All right, you have to go back to Cal 2 to derive that, but that is what it comes up being. Now let's see what we can do to make things simpler here. First thing let's do is do 3 into 3 to wipe that out. Okay, and let's do a 2 into 128 will be 64. 4 will go into 64 16. 2 will go into 16 8 times. So what we wound up with is 8 pi over root 2. Now, if you don't like having the radical in the denominator, you could rewrite that as 4 root 2. I can't erase. There we go. Okay. 4 root 2 pi. Okay. All right. That's exactly what they got. 4 root 2 pi. Now that's a pain in the neck, okay? Most of that is algebra, which made it such a pain. But part of it was calculus. Wallace's formula was definitely calculus, and they referred to that. Otherwise, you're going to have to use the recursive formula in the back of your book or front of your book or wherever you find your tables. And so Wallace's formula really makes it go by much quicker. But sure enough, that's what we got. That is the correct answer. But going back to the very beginning, you have to set up your triple integral, or your double integral, 1 dx and 1 dy. I chose the dx because that was 0 to 2. Otherwise, the last one would be 0 to root 2, which would have been okay. There's nothing wrong with that, okay? But I just like 0 to 2 better, okay? And then recognizing how these things are similar and they break down and can be subtracted pretty easily. That's part of that last step, early step, very early step. And just got through it. It's all there is. Also the form up there subtracts pretty easily and ultimately make the trig substitution to get it to thetas, calculate what your thetas will be, and that was pretty easy. And once you've done that, you're looking up and using Wallace's formula. If you don't do that, you got a lot more work to do. All right, I know that was a pretty complicated type problem. Any question on it? Okay, your book explains it fairly well. Okay, now, we got another one, not in some ways similar to it, but other ways a little bit different. And that is example 4. Now, the good news on this one is you can all go to larsoncalculus.com. That's a free website. Anyone can go there. Your grandmother can go there. She doesn't need to be in the course or anywhere else. You know? larsoncalculus.com and see an interactive version of this type of an example. You can actually interact with it. So here's what the deal is on this one. Find the volume of the solid region bounded by the surface f of x, y, or z is equal to 3 to the minus x squared. Okay. Now that's the surface. Now what's a little bizarre about this problem is that notice it's a function of x and y, but you only see x's in the function. Y is completely arbitrary, okay? But it is a surface, okay? Now let's see where it tells you. And the planes, z is equal to 0, so that's the base down there. Y is equal to 0, so that's that backside. Y is equal to x, that's as far as you're going there, which could be variable, but x is only going to 1. So y is going from 0 to 1, x is going from, they don't say, do they? Now they show it in the figure, And all right, let's see. They have a limit on, no, a back limit on y, a front limit on x, and a side limit on x. That's right. Okay, so actually the back limit on x, front limit on x, and then the y 0 is the back limit and x is the front limit. Okay. All right, I think I've got it down. Now they want me to draw this, and I have a really tough time drawing it. Okay? But you almost need it for what you got here. So let me again give it a shot up here. And this is going to be pathetic, I'll tell you ahead of time. So here's your x, here's your y, there's your z, which they call just f of xy. Okay? E to the minus x squared. Okay? Well, let's draw in our other lines here. Z is equal to 0 is a plane down here. Okay? Y is equal to 0 starts here, so y doesn't go any negative. Y is equal to x, that's the line that comes out here. And x equal 1, that ends right there. Okay? So here is the base of that thing. Okay? And when x is 0, your z up here is 1. Okay? So it's coming down like this, down like that, down like this, you know. X equal 1 goes across something like this. X equals 0. Okay. It intersects here. So basically it's going to go 0 to 1 on y, 0 to 1 on x, but it's in this portion here. But this is a curve, okay? And it's coming down to the base down here somewhere. Now that's really ugly. It's just totally ugly. I'm going to take out one line because really put one too many in there. Okay. This is not a good representation of it, but it gives you enough to go on. Your base down here is x equal 1, y is equal to 1 here, and here's your diagonal for that, which basically is the square root of 2, is the length of that. But we don't really need that, but just to give you an idea, there is the triangular base that you have. Okay? Now, the question now is, do you do dx's or dy's? And I just get the feeling that dx's are going to be the best thing to do last. So let's do, I'm sorry, I did it wrong. dx's are the best thing to do last. So let's do our dx this way. Okay, there's your dx. And it's going from y is equal to 0 to y is equal to x. All right, so here's your integral. That last one is going to be x going from 0 to 1. Your middle integral is going to be y is going from 0 to x. Okay. Then you have your e to the minus x squared. Okay. your first integration is going to be your dy integration, and your last one's going to be your dx integration. Now, yeah, I think that'll be okay. I'm real tempted to make the dx first and then the dy, just so you can get rid of your x's altogether. Let's see if the book did that. No, they did it last. Okay? I was thinking that probably would be best just on our limits. But anyway, we got it. So this is your integration. Setting it up is basically one piece of the tough part of it. Now, here's what we're doing here. You see, your last d's are going to be your dx's, and you're going to sum that 0 to 1. But before that, you're going to split into dy's, and that is going from 0 to y is equal to 0 to y is equal to x. From y is equal to 0 to y is equal to x. And that goes on the outside, and then your z is equal to yeah, I think that's just the way to go. All right. So let's do the first integration with respect to y. What would that be? We're not going to do the last with respect to x, 0 to 1. And what will this be? Antiderivative of e to the minus x squared with respect to y. E to the minus x squared y. The y is, this is all treated as a constant because you're taking with respect to y, but you're going to evaluate y equals 0 to y equal x. Okay? And then, ultimately, we'll do our dx integration last. So we're going to plug in for the y, x, and we're later going to plug in 0. That's not going to give us anything. So this is going to be the integral from 0 to 1 of e, okay, I'm going to put the y and the x out front. That's going to be x e to the minus x squared. Sort of got lost there. Okay? And when you do the minus 0, that doesn't give you anything. And then you're going to integrate this with respect to x. Thank goodness, because before, this form, with respect to x, doesn't have an integral. That's one of those non-elementary functions. You can't integrate. But when you put the x in here, which you got from here, now that makes it something you can integrate. What would be the technique you would use to integrate that? Okay. Well, it's kind of like undoing the chain rule, which is substitution. Simple U substitution. Okay? Now, the most complicated looking part here is that minus, the innermost part of the most complicated part is that minus x squared. So what we're going to do, I'm going to write it up here. Let u equal minus x squared. Then, du is equal to what? Negative 2x dx. Don't forget your d. That always has to be there. Well, we don't have a negative 2x dx. We just have a x dx. So let's divide both sides here by negative 2. Okay? And that will make the du over a negative 2. Okay? Now, we're also going to change our limits because u is equal to minus x squared. So when x is equal to 1, x equals 0, u is equal to 0. And when x is equal to 1, u is equal to minus 1. And that's a big boo-hiss because now you have the smaller number on top. We're going to change that in a minute, okay? And rather than dx like we have here, or x dx like we have here, that's going to be a minus du over 2. So I'm going to put the minus 1/2 out front, the du in here, and then we've got, I'm sorry, I didn't leave enough room. Okay. All right. The du is minus 1/2. That's in the front part. The x is incorporated in that, and this would just be e to the u then, because we did it minus u. Okay. Now we've got to change some things on that. For instance, you need the minus 1 in front, at the bottom, to 0. But if you do that, you lose the minus sign. So you just got a 1/2 e to the u du. Now, that's a pretty easy integral to evaluate. What would that be? Okay, that would be e to the u. That's exactly what it is. Okay, and you evaluate that from minus 1 to 0. I don't know where my minus 1 went. Okay, minus 1 to 0. And now you plug those in, and you get 1/2. E to the 0 is 1 minus e to the minus 1. Okay, and that's your answer, I hope. Okay. Now I've got a little bit of a problem here. Let's see if it resolves itself. Oh, that's right. Okay. They wrote in the book minus 1/2 1 over e to minus 1, which is exactly what this is. Then they did some other mess to it, and here's what they did. And this isn't necessary to do, but I'll do it just because they did, just so you can see how to make these answers reconcile each other. Okay, this is the same as 1/2 times 1 minus 1 over e, right? Which is 1/2 times e minus 1 over e, which you could say is 1 over 2e times e minus 1. And that's what they got. And if you plug that into your calculator, e is about 2.7 something another, so this will be 1.7 something another, and then divide that by 5 point something another, and they say you get about 0.316. I don't have a calculator, so I can't check them on that, but I hope they're right. Okay. So that's example 4. Okay. Now, the calculus part of it, the worst part to me is drawing the figure. Okay. The tough part of the calculus part is figuring out where to do the d, which order to do your d's, dx's and dy's. And I sort of go with, it's pretty obvious to me that the x's here are going 0 to 1. That sounds like to be a good last thing to do. And then your d's in between that, so there's your dx. You're going to have all those. And then between that, you've got your dy's. y is going from this line here, which is y is equal to x, back to y is equal to 0, right there. So that's set up perfectly for that. So your y integration is going to be from 0 to x dy. Your function is just this thing, okay? Now, sort of the bad news is, well, it's not bad news. There's no y in this, so you just this times y is that integral. Then you plug these values in, and you get a e to the, or x e to the minus 2x, okay? And that's what we got here. E to the minus x squared is what I meant to say. And then you do a u substitution here, and get that to be minus 1/2. Now, the bad news there is it reverses your order of, puts the negative number on top, so you have to flip it, but that loses the minus sign that you had picked up, so you're in better shape there. And then the integration is easy, and then the rest of it is just figuring out the thing. So setting up the problem, which sometimes includes graphing it, and then figuring out the order of integration and what it's going from and to. And this one actually worked out pretty easily. This next one, however, has potential to be a real bear. Any questions before I delete this? Okay. All right, let's see if we can get this one done, maybe before we take a little break, because I'm running awfully dry right now. So here's a volume of a region bounded by two surfaces. So find the volume of the surface of the solid region bounded above by the paraboloid. Z is equal to 1 minus x squared minus y squared. That's an elliptic paraboloid. Okay? And below by the plane z is equal to 1 minus y. No x dependence at all there. Okay? Now, if this required a picture, I'm in really sorry shape, okay? Because these are not easy to draw, okay? I'm probably going to wind up trying to. Do all of you have a book or something you can look at to see it? You don't, okay? So I feel like I probably do need to draw it. But before we do that, if it would be kind of nice to know what our limits of things are going to be. And I guess the picture is going to be necessary. So let's try it. Okay, x, y, and z. Okay. Now the paraboloid's going up to 1. This will be going out to 1. That'll be going out to 1. Could be going to -1 here and a -1 somewhere out here. Okay. Now, the base of this paraboloid is actually a circle. It's not an ellipse. It's a circular paraboloid. And where z is equal to 0, you have x squared plus y squared is equal to 1. So this is going from here to here to here to here. So basically, this is a circular base here. Okay? And then it's going up to, okay, there's your paraboloid. That wasn't too awfully bad. Okay? Now the plane z is equal to 1 minus y. That means the x is going to be going any value for x, as long as that fits. So let's pick a few points here. When y is equal to 0, z is equal to 1. So it goes up here to the top of this thing. And when when z is equal to 0, y is equal to 1. So it's going down here. Okay? Now, here's your paraboloid that sticks up out here. Here is your plane line that goes through like that. So it's cutting off part of this. That's the part we're interested in. This part that's under the paraboloid but above that plane. But now this plane, and this is sort of a tough part, it goes over here and it comes over here. Okay? So you have a variety of thicknesses here. And this, my picture isn't helping me at all. I don't think it'll be helping you any either. Okay? But let's see if we can figure out some points of contact here where these two things are equal. Okay? So let's just set these equal to each other. They're both equal to z. So let's say 1 minus x squared minus y squared is equal to 1 minus y. Okay? I'm not just sure this is the best way to go on this. Yuck. Alright. My pen drug, I didn't even realize it. Okay. All right. Set those two equal to each other. And the first thing you can do is subtract the ones away. Okay? And that leaves you, I'm going to switch sides here. I think, and I have x squared is equal to y squared minus y. Okay. Okay. That certainly seems to be a form that's somewhat elliptical in shape. Okay? If you completed the square of each of those, what you would have is this. X squared is equal to y squared minus y. No. Okay. Clean it up a little bit more. Plus minus. Okay, now I'll explain what I'm doing in a minute. Okay? You take half of this coefficient, you're going to complete the square. Half of the coefficient is 1/2. Square it, you get a 1/4. 1/4. But you just changed the problem by adding 1/4 to it, so now we're going to subtract 1/4 so you have the same issue. Okay? Now this becomes x squared is equal to you know, I messed something up. Let me back up. Let's see it now. My line here almost obscured me to the fact. These have to be on the same side. Okay? Let me go back. I'm sorry. I knew something looked wrong, but I couldn't figure out what it was until I noticed my signs. Okay. A lot of it's going to be the same, but a lot of it isn't. Okay? Now, with those two things in mind, That's an equal sign there. I don't know what happened to that. Okay. Set those equal to each other. Subtract off the ones. Everything's negative. So let's change that to x squared plus y squared. And then that becomes a plus, but we're going to bring it over here. Plus y is equal to 0. Okay? And this is where we do x squared plus y squared minus y. And this would then be plus 1/4. If you take the 1/2 and square it, and then so this has to be equal. Why not equal to 1/4? See what that'll do. Okay, so this will be an x squared plus y minus 1/2 squared is equal to 1/4. Now let's multiply everything by 4, and you get 4x squared plus 4 times y minus 1/2 squared is equal to 1. Okay, now that's more of the ellipse I was thinking. Okay, that's that ellipse up there. Rather bizarre in that it's an ellipse at an angle is one thing. Okay. Let's see. Let me make sure I'm not chasing down a rabbit somewhere that I don't need to be. Okay. Now, I've got the same thing they do, they just did it in a different order. Okay. Now, what you may or may not see here, and I didn't see it at first, but it's sort of making sense now, is that this ellipse that we see here, which is hard to deal with because of the angle of it, if you project that downward toward the plane, and I can't quite for the life of me decide, but they say that projects onto a circle in the plane, in the XY plane. Now, I know that this base of the ellipse is a circle, and I'm trying to figure out why this plane also makes a circle. Part of it comes from this concept here. The same thing we got, x squared is x squared plus y squared minus y is equal to 0. And they rewrite it this way, as x squared is equal to y minus y squared. Now, even written that way, that does form a circle, okay? The circle is centered at 0, 1/2, 0 on x, 1/2 on y. And have I drawn this thing? No? Yeah, 0 for x, 1/2 on y. Yeah, I said that right. Okay, that's what this tells us. And the radius of that circle from this thing right here is 1/2. Okay, so yeah, that does work. A circle of radius 1/2. Okay. It was right there in front of me, but I wasn't quite figuring it out. So this is a circle of radius center 0 at 1/2. It should up there it is 0 at 1/2. And the radius of the circle is 1/2, because that's r squared. So that is projection down onto the xy plane. Okay? So from that projection, now we can, okay, there's part of this ellipse, and that's what we're looking for, the volume that is above the, bounded from above by the paraboloid up here and bounded below by the plane, which is down there. Okay? Now, how they suggest that we do it is picture this as a cylinder here. Okay? It's got a slanted top to it, but we're going to take that and below the plane is exactly a cylinder. It's cut off some. Above the plane is the part we're really interested in. So we're going to do the whole thing under the paraboloid minus the thing under the plane, which is a portion of a cylinder. Okay? So, in both cases, we need to do our dx's and dy's. Now we got to figure out how to do it here. And everything on here is going to be symmetric about the y-axis. So I would say let's go 0 to 1/2 on the y. So your last integration here is going to be your dy as you go from 0 to 1/2. Let's see how that works out. And your first one is going to be splitting this into those pieces as your dx goes from we need to solve x as a function of y, and that's not going to be too bad. X is equal to the square root of y minus y squared. Okay? Now, on the one, oh yeah, okay. We're going to have to go from minus to plus. We can't do just half of it. We can do the half from the y-axis this way and double that, but we can't do half this way because you see up here there's a lot more involved than there is here because of the slope of that. Okay, so your last integral, the y is going from 0 to 2, 0 to 1/2. That's going to be the sort of easy one to do. You're going to have to double that. But the other part is going from one end of this to the other. So what I drew as a single, I probably drew it the wrong way. Yeah, I did. Okay. The x's are going to be expressed in terms of y, and that's going to be plus or minus. You're going to have to do the plus or minus. So, our integral of this thing, and there's Tevin, lost some and gained some. Tevin's here. It's been so much of rotating door here, it's hard to keep up with how many are here. So, what is this integral going to be? All right. It's actually going to be two integrals. The integral below the paraboloid, okay, that's going to be 1. here is the paraboloid here, okay? So it's just going to be that integral minus the one below the plane that's inside the paraboloid, okay? That's the part that's, and everything's going to be along those lines here. So it's going to be a double integral for both of those. And let's do the paraboloid first. Okay, I'm going to bring this in some because I'm going to need all the room I can get. Am I going to erase anything else? Probably, but not yet. Oh, that's not what I wanted to do, the pen. Okay. So let's do the integral. Double integral. The dx's are going from minus the square root of y minus y squared to the square root of y minus y squared. That's going to be these going along here. I hope I'm saying this right. No, that's your dy's. Sorry, that's the dy's. Okay. Those are going this way. Okay. This is your dx here, and the dy's are going from 0 to 1/2, but you're going to double that. Yeah. Okay. Now, the first part, we're doing that part. So that's going to be 1 minus x squared minus y squared. That's your paraboloid. What's underneath your paraboloid between those limits. Okay? No, I've got these backwards. Sorry about this. I keep seeing it as backwards, but then all the things seem to fall into place well. The dy's are going from 0 to 1. I should have seen that. And you don't have to double that one. Okay, so wait. Well, I can't get my eraser to work. There we go. And you don't need to double it. That's just 0 to 1. That's your last one, the dy this way. Your x's are going the dx's are the ones you can double. So this you can go from 0 to 1 here. I'm pretty sure you can. We'll see. And that we will double. Okay, that's the one. The book doesn't do it this way, but I think you can. Okay. Because the dx's are the same on this side as they are on the back side. So yes, you can do that just from there. And the dy's are then going from 0 to 1. Yeah. So this one, if you extended them back here, they're the same on the back side as they are on the front side. So that will help us there on symmetry. Okay, that's the first part. Minus the one under the plane. So under the plane, we've still got the same limits here. 2 times 0 to the square root of y minus y squared. and this will still be 0 to 1. But now you just do the part on the plane, 1 minus y. And again, your order is dx, dy. Do the dx first and the dy second. Okay. Now, the thing that since you have the same limits on the integration, you can combine those together and they've done something confusing in the book. They've got the first one done right, and they've set up to do the second one right, but on the next line, they only do the first one. No, they don't. They combine them. Okay, we'll get to that. All right, so this is 2 times the integral from 0 to 1. Okay, and let's do this integration first. What is the integral of this thing right here? This thing right here, 1 minus x squared minus y squared with respect to x. Okay? What is the antiderivative of 1 dx? X. Minus what? X cubed over 3. Perfect. Minus times x. Perfect. Okay? Now, you got the same thing on the other side, so let's just go on and do those two. There's another, only this is a minus x, right? And then you have a plus yx, because minus and minus makes it plus. Okay? Now, and that's going to be evaluated from 0 to the square root of y minus y squared dy. Okay, now I need some room to work here, so I'm going to go up here, I think just right up here and rewrite this. 2 times the integral from 0 to 1. Okay, now here your x's go out. Okay, and that leaves us a minus x cubed over 3 minus y squared x plus y x. Okay, now let's see what that's where they kind of lose me in the book. No, we've done it right. We're exactly there. Okay. It's just, they did it in such a strange way in the book. I guess what they did here was first subtract, and they lost the ones first, and then they had minus x squared minus y squared plus y. So that's what they did. I see. I was wondering why they didn't do it that way, and that's what they did. And that's exactly what we've got here. And they're evaluating this from x equals 0 to x equals the square root of y minus y squared. Now plug that in for the x's here, and then you finally have your dy out here finally, but we haven't gotten there yet. So let's do that. Now I think I'm going to erase my drawing if that's okay. It's ugly enough. So let's try to get rid of that. I think we used it for all we could, and it won't erase well. Man, this is hard to erase. There we go. All right. All right, let's plug and chug and see what we got. 2 times the integral from 0 to 1. Now when we plug for x in this thing, this is going to give us a minus y minus y squared to the 3/2 power over 3. Okay? Minus y squared times y minus y squared to the 1/2 power. Okay, now let's back off for just a moment here. We got the same situation coming up this time that we had last time. So let me, before we do that last step that I just did, let's notice here that we can factor out an x here, and this will be a minus x times y squared minus y. Or make it a plus x times y minus y squared. I think that would even be better. Okay, what we did there, this one's to the 3rd power, but these, the x's are to the 1st power. And if you'll notice, that's plus x times y minus y squared. And that y minus y squared is the same thing you got inside the radical there. So if we do that one that way, then this will be y minus y squared times x. Well, x is the square root, so this will be a plus you're plugging that in for there, so it would be y minus y squared to the 3/2 power, because this is to the 2/2 and x is to the 1/2, so that's 3/2. The zeros go away, and that leaves you a dy. Now again, this is this thing minus 1/3 of this thing plus 3/3 of that thing, so this is going to be 2 times the integral from 0 to 1 of 2/3 of this, so let's make that 4/3 here. Okay, 4/3 of y minus y cubed to the 3/2 power dy. Okay, we pulled the 2/3 out because it was minus 1/3 plus 3/3, so that's minus 2/3, or 2/3 on the outside. Okay, now that, by the way, is a square. I don't know why it showed up as a 3 there. Y minus y squared. Okay. Now, that's not a particularly pleasant thing to do either. And by the way, we're right at the same place they are here. And they don't say how they did this integration, which is really bums me out. Let's see if we can see any way possible. Did they just go to a table or something like that? It's not a sign. Let's just rewrite that as y times 1 minus y to the 3/2. I think a substitution will do for you. Okay, it's a rather weird substitution, but it will. Let's try this at first. Let's let u equal y minus y squared. I don't like that one. Okay, so let's not do that one. Let's do u equal 1 minus y. Well, that seems to be a bit strange to do, even to me. And I'm doing it. Okay. Then du is equal to minus dy. Okay? But you also have here that produces y is equal to 1 minus u. I'm not sure this makes it any better. I think I'm going to have to go to the tables and see if we can find an integral that will work. Okay. Y minus y squared to the 3/2 power. I see nothing like that in here. I guess what they do is complete the square or something. Rather than waste any more time on it, I guess that's what they do, is completing the square. But I don't even see how they do that. So I say let's just let that one go. I cannot see how they went from their fourth step to the fifth step. I bet you it's true, but I don't see how they did it, and they didn't show enough to reveal that. So let's just can that one and move on to this one, average value of a function. Sorry I took so much time on that. The principle is good. It's the execution. When they got down to that integral, I just don't see it. Okay, let's start over here. For a function f of one variable, by the way, we just passed our normal break time. Do we need to take a break? I see we've already had some people break already. In fact, they may not be coming back. Y'all need one? You don't? You do? Like to have a break? Okay. Let's do it. I'm sorry that one took so long to have absolutely no benefit from it. All right, as soon as we get projection back, we'll pick up and go. Talking about the average value of a function. For a function of one variable, f in one variable, the average value on an interval, this is just to remember it, okay, is the length of the interval, b minus a, 1 over b minus a, times the integral, the value of the integral. So it basically summing up all the values, dividing by the length, the average value. Just like you do your test. Sum all your tests together, divide by the number of tests, which is similar to the length. Given a function f in two variables, you can find the average value of f over the plane region R as shown in the following definition. Okay? Now, if f is integrable over the plane region R, then the average value of f over that R would be, or should be, 1 over the area, whereas this was 1 over length, 1 over the area R, and then the double integral of R over R of that function, okay, times dA. This is usually your dx dy. Okay, thank you. All right. Now, where A is the area of that region R. Now, if that's a nice rectangular region, that's hunky-dory. If it's not, if it's an irregular shaped thing, then you've got to do your area by another integration. So we'll take a look at that. Here's example 6. Find the average value of this function, f of xy, which is 1/2 x times y, over the plane region R, where R is a rectangle. Thank goodness, that's going to be really easy to do. The rectangle has these vertices, 0, 0, and 4, 0. So that means on the x-axis it's going from 0 to 4 with y equals 0. I'm sorry. Y equals 0 would be the x-axis. No, yeah. Y equals 0 means you're on the x-axis. So you're 0, 0 to 4, 0 along the x-axis. 4, 3 on the y-axis. So where you're 4 on the x, you're going to 3 on y. Okay? And then 0 to 3, same thing here, 0 to x to 3. So everything, it's just a nice straight rectangle. Now, you know the area of that rectangle, right? 4 by 3. 12. Okay? So there is the area. You don't have to do anything more from it, nothing esoteric. So the area of that rectangle is equal to 4 by 3 equal 12. Okay, 0 to 4 on x, 0 to 3 on y. So 4 by 3. All right? Now, the bounds for x are, of course, 0 to 4. And the bounds for y are 0 to 3. Okay? So the average value of the function, from what we just had, average value of the function, okay, would be 1 over 12, that's the area, times the integral of this function. And I'm going to pull my 1/2 out, so this is going to make the 1 over 24, okay? And it doesn't matter which order you do these, so do them either order you want to. 0 to 4, that would be the dx's, and 0 to 3, the inner one would be the dy's. I pulled the 1/2 out front, xy. Okay? So that's pretty easy to set up. So it's 1 over 24, okay? We'll hold off on the last one till a minute. Let's integrate the first one. With respect to y, what will that give you? Antiderivative of xy with respect to y. X. A little louder, I can't hear. X what? Okay, I still can't quite hear. Okay. No. Integrate this with respect to y. You treat x as a constant, so that's just x. What's the antiderivative of y? Y squared over 2. Perfect. Okay? So that would be y squared over 2. And you evaluate that from 0 to 3. Okay? And then you're going to have your dx. What you were trying to have earlier, right? Okay, now, because of that over 2, you can pull that outside and make this a 48 now. We keep pulling more things out. Now this, by the way, was your y value. So y equals 3, y equals 0. Okay? So let's evaluate that. 1 over 48 times the integral from 0 to 4. That's going to be the x values. Get out of there. Okay. Now, let's plug in y equals 3 here. Now that's a 2 there. It looks like a 3, but it's not. It's x, but what's... That would be 9. 9x squared minus 0. So, I mean 9x minus 0, and then your dx. Now that's a pretty easy one to do. What would that be? 1, well, let's pull out the 9. 9 over 48, which by the way you can reduce to make 3 over 16, right? Okay. And what's the antiderivative of x dx? X squared over 2. Evaluate that between 0 and 4. If I can get the 4 to show up without going to a new page. Okay. So this will be 3/16 or, no, I'm not going to do it this time. No, sorry, hit the wrong key. Okay. 3/16. Let's just evaluate this. 4 squared is? That would be 8. 16 over 2 is 8. And then the 0 doesn't contribute anything. Well, 8 will go into 16 twice, so this will be 3/2. That should be the average value of that function over that range. After that last one, this is a beautiful problem, right? All right, let's clear what we've got here and see how they do it. The area of the rectangular region, A, is 4 by 3 is 12. We saw that right off the top. Okay? And there they show it. I'm glad I didn't have to draw that. But as this is going up to a point, 4 times 3 is 12, after that is 6. So this is going up to the point of 6 there. That's rather bizarre looking graph, but it's true. The bounds for x are 0 to 4, bounds for y are 0 to 3. We saw that. So the average value is 1 over a, which we know to be 12, the double integral over that region, rectangular region, of alpha of x, y, dA, where the dA is dx, dy. Okay? And the function that's 1/2 xy, they did do y dx. It really doesn't matter. I think that's what we did too. That 1/2 can come out here and join the 1/12 and make it 1/24. And see if they do that. No, they leave it in there. I don't know why. But they do integrate with respect to y, which makes another 1/2 x. You have the 1/2, then you have x, y squared over 2, so that makes 1/4 x, y squared. That's what they got there, okay? And they've got to evaluate that from, because you're integrating with respect to y, the y's, I like to write it in, y equals 0, y equals 3, so you know only to substitute there, you don't accidentally substitute there, okay? So this is going to be 1 over 48, and this is going to be 9, so that would be 9 over 48, which is our 3/16, and that's what you're integrating 3/16 antiderivative of x dx from 0 to 4. Well, they pull out the 9/4, which is fine, and do the antiderivative of x dx, and that would be 3/16. They finally did it, and that would be 1/2 x squared evaluated from 0 to 4. We plug a 4 in for the x, and you get 16, and that gives you 3/2. Or 3/16 times 8, which is 3/2. All right, good. Whew. Finished 14.2. Homework exercises here, either 3 or 5. They're both at Calc Chat. 3 is at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. Any of the odds 13 to 19, they're all at Calc Chat. 13's at Calc View. Any of the odds 21 to 25, they're all at Calc Chat. 23's at Calc View. 27's at Calc Chat. Any of the odds 29 to 33, they're all at Calc Chat. Any of the odds 35 to 39, they're all at Calc Chat, where 35's at Calc View. And good luck with that one, because that's another one like we did on the last one. Hopefully it comes out a lot better, cleaner. Not the last one, but the previous one. Okay, then any of the odds 41 to 43, they're all at Calc Chat. 45 to 49 are at Calc Chat. 51 to 55 are at Calc Chat. 51's at Calc View. 57's at Calc Chat. 59's an exploring concepts. You can do that one if you like. It should be at Calc Chat. There's some probability questions, 61 or 63. They are at Calc, should be at Calc Chat. 65's a proof. It should be at Calc Chat. 67's an approximation. It should be at Calc Chat. And there's a true false 69. It should be at Calc Chat. And then there's 71's a maximizing a double integral. And finally 73 gives you an average value problem. So they both should be at Calc Chat. All right. Now, I do not think that anything was required for us to do on polar coordinates. So I'm all in favor of skipping that one. And center of mass. I don't recall that we need anything there either. Well, actually what it gets down to, the other times I've taught this course, we haven't made it this far, so that's what I'm going by. So goodness gracious. We're not going to do all of 14, that's for sure. Okay. Let's go on and do change of variables for polar coordinates. It's not a long section at all, so maybe we can knock it out pretty quickly. Okay? So, okay, and you do know about your research paper, right? Okay, I just want to make sure you knew, because you came in after I said something, so I'll make sure you had heard that. All right, if the PowerPoint will ever open, we're going to get there. All right, here we go. Start from current slide. Okay, chapter 14 is still multiple integration. This time we're going to do a change of variables for polar coordinates. We'll write and evaluate double integrals in polar coordinates. In x's and y's, they're pretty simple. Dx, dy. Okay? In polar coordinates, though, where you have r and theta, you only have one of those with a dimension. That's r. You need to cover an area, so you need a second dimension. And that's sort of the little trick that you have to do with polar coordinates, is what that is. So let's look at double coordinates and polar coordinates. Double integrals and polar coordinates. I can't talk. Polar coordinates, r theta, of a point are related to the rectangular coordinate with xy as follows. And this should be old hat. X is equal to r cosine theta, y is equal to r sine theta. That's if you know your polar coordinates, you can get to xy coordinates, rectangular coordinates. But if you know rectangular coordinates, r squared is always x squared plus y squared. So this gives you r, square root of that. That's Pythagorean theorem, basically. and this is your definition of your tangent. Y over x is your tangent theta. So arctangent of that will give you your theta. So the square root of that gives you r, inverse tangent of that gives you your theta. All right. Now with those in mind, those are going to be helpful when we are doing your going back and forth. So here's example 1. Use polar coordinates to describe, that's all we're doing now, describe each region shown in this figure. So here's this region R here. How would you describe that in polar coordinates? Your R is going from?
From 45.
Say again?
I said 45 degrees.
Okay. Okay. I just drew that one with my finger, but where is it going? What is the R?
That's
Okay, okay. What is your R all along there? Second? The radius, and what is your radius?
That's the half.
What is the radius? 2. Okay. So how you would describe this was, let me get my pen back. Okay. That would be 0 is less than or equal to r is less than or equal to 2. Okay? And how about theta? Where's theta going from? Theta is an angle. What's the angle there? 0 to? Or pi halves. Usually we deal with radians. So here the 0 is less than or equal to theta is less than or equal to pi halves. That's how you would describe this region in polar coordinates. How would you describe that region in XY coordinates? Oh boy, that would be somewhat difficult because you know that x squared plus y squared is equal to 4. That would certainly be there. That would be your r squared. But you would have to have, say, if you did the dx at the end, then the y is going to be 1 minus x squared. I mean, you'd have radicals and all sorts of things there. This is really simple with polar coordinates. Okay, how about that next one? How do you describe that in polar coordinates? No? There is no r equals 0 here because that's inside the donut. Okay, 1 is less than or equal to, r is less than or equal to 3. Right? That's it. For all theta. Theta is, you can write it down if you wanted to, 0 less than or equal to theta is less than, that's supposed to be a theta, not a whatever that looks like. Okay. Less than or equal to 2 pi. Because you're going all the way around. You don't have to write that, but you could. All right, that next one's rather bizarre, isn't it? Okay. How in the world are you going to describe that? Now. All right. When theta equals 0, you're at the point 3, 0 is on this. 3 is r, and theta is equal to 0. It's going up to 6 pi halves, down to minus 3 pi, and then comes around to 0 pi 3 halves pi. Okay, So that's a rather strange looking bird there, but there really is a pretty simple description of it. XY coordinates, hang it up. That's going to be almost impossible to describe an XY coordinate. Okay? Now, rather than spend too much time guessing at it, let's just see how they do these. The first one is a quarter of a circle of radius 2, so that would be described in polar coordinates as the region is a set of all r theta such that 0 is less than or equal to r less than or equal to 2, and 0 is less than or equal to theta is less than or equal to pi halves. Exactly like we said. We didn't write it in set notation, but we could have. Okay? The second is a region consisting of all points between concentric circles of radius 1 and 2 and 3, so that would be described in polar coordinates as this region, the integral, the set of all r thetas, such that 1 is less than or equal to r is less than or equal to 3, and 0 is less than or equal to theta is less than or equal to 2 pi. Okay? Carlton's here. Good to see you. Well, there you are. Couldn't find you for a while. Okay. Now, what we're doing is polar coordinates. This is in Chapter 14, Multiple Integration. 14.3 is change of variables in polar coordinates, and we're on example 1 on page 990. Now, we got those two. They were pretty easy. They were the first two there. That third one is somewhat of a bear. So what we're going to do is look and see how they do the third one here. Okay. The region is called a cardioid because it sort of looks like a heart. Cardio, okay. And your A equal B equal 3. Now, where in the world did they get A and B? Okay. Now, obviously, they've hit these and talked about them somewhere before. And I don't know where that is. Possibly back in chapter that we did this in Cal 2, long time ago. Polar coordinates. Yeah, if you go back to chapter 10, or if you got another book, some special polar graphs are your cardioids, okay? And they're real, it's not completely obvious how you get those. And here's what they're referring to. If R is equal to A plus or minus B times either cosine theta or sine theta. Okay? I think it's, so this is R is equal to A plus or minus B, either sine theta or cosine theta. We have to decide which. Okay? Now here's going to be the dead giveaway. Okay? When theta is equal to pi, 3/2 pi, which is down here, then you're at 0. Okay? Theta is equal to 3/2 pi, you're at 0. So that gives me the suspicion that we're going to be dealing with cosine theta, not sine theta. Sine theta is 0 at your whole pi's, not your half pi's. Okay? So that is the first part. The second part is the A and the B. Well, when they add, they're going to go to 6, and when they subtract, they're going to go to 0. So that would indicate, and that's where they're getting the plus or minus 3, okay? But they sure didn't have it anywhere thing. So here we're going to be A equal 3, B equal 3, and then we're going to use a cosine theta, I believe. Let's check and see that. So that would be R is equal to 3 plus 3 cosine theta. Now that doesn't quite seem right, but let's give it a look and see. Okay? Now, when theta is equal to 0, which is this way, cosine is 1, so I've got it wrong. That would be 3 plus 3. That's your 6. So maybe we do need it to be sine theta. Let's try that. Okay? This is not, I've never taught from a calculus book that went into this much detail here. Okay? So when theta is equal to 0, sine theta is 0, and that would give you 3. So that makes sense. When theta is equal to pi halves, 3 plus sine pi halves is 1, so 3 plus 3 is 6. That's looking good. When theta is equal to pi, you're over here, that's minus 3. Wait a minute. Theta is equal to pi, that's 0 again. And that gives you a 3, and we should be at a minus 3. So that's not quite right either. Okay? So we're just going to have to see what they say. Okay, they say A is equal to B is equal to 3. It can be described in polar coordinates as R is equal to 0 set of all r theta such that 0 is less than or equal r is less than 3. I'm sorry. 3 plus 3 sine theta, and theta is 0 to 2 pi. So we had it right, but why wasn't it showing up right? I don't know. Okay. I'm not going to waste any more time with this because this is, to me, the key stuff here. So let's just go through it quickly. The regions in example 1 are special cases of polar sectors. The first of those was, here you're going from R1 to R2. You're somewhere in here and going from theta 1 to theta 2. So there's your little, what used to be a grid for XY is now a sector here. Okay? The R1's going from, R is going from R1 to R2, and theta, that's your delta R, and your theta is going from theta 1 to theta 2. That's your delta theta, the difference between that. Okay? Now, so that's called a polar sector. So when you're doing double integrals, that's what you're going to have. So to define a double integral of a continuous function, z is equal to f of xy, in polar coordinates, this is in rectangular coordinates, consider a region R bounded by the graphs of R is equal to g1 of theta, so that would be this one, some sort of graph, and g2 is up there, and the lines theta equal alpha and the theta equal beta. So those are the regions. Okay? Instead of partitioning R into small rectangles, we use partitions of small polar sectors. So your delta R sub I would be something in between your G1 of X, G1 of theta here, and G2 of theta there. Okay? That's your, you split that into so many R units there. And to do your thetas, you go from theta alpha to beta and split that into so many. Now they seem to do 1, 2, 3, 4, 5, 6. splits there, and 1, 2, 3, 4, 5, 6, 7, 8, 9 or so splits on R. Okay? And on R, superimpose a polar grid made up of rays and circular arcs is shown here, and then deal with each one of those things. This is how you do your base that was in your XY plane here. Now it's in the R theta plane, and then you're going to do some surface that's above that. All right. Now, you double the polar sectors RI lying entirely within R form an inner polar partition, and we call it delta. The norm of that is going to be norm of delta, the maximum length of the longest diagonal of the polar sectors. So if this was it, that would be this one or that one, whichever is longer. They look like they'd be about the same. That one or that one. Okay, whichever the longest one is, that will be your polar sector. And these, it's almost always going to be the outer ones because those are wider. They're the same thickness this way, but wider that way. Consider a specific polar sector, R sub I, shown here. That, okay? So you're going from R1 to R2 on the R's, from theta 1 to theta 2 on the thetas. That's your polar sector. Some point in there is that is defining your R1. Can be shown that the area of R1, okay, now here's where things get a little trickier. The area of that little delta A sub I, that little sector we had, is R delta theta. Now why is that extra R in there? Well, one reason is you need two dimensions to find an area. Theta is not a dimension, it's a ratio, okay? You need a dimension. So what you do with, the R is how far you are from here, okay? And then the theta is based on that R, what your delta theta is, okay? So that gives you basically the length this way. Because see, an R down here is going to be a shorter length than, an R down here is going to be a shorter length than the one up here. So you need to know what area you're in, and then your delta theta, that gives you the size of that. So your polar sector is what going to depend on dr. Those look like they're about the same, but the theta is going to be r times d theta, because the further out you get, the bigger they are. See, if you're way down here, they would be incredibly tiny, okay? Way up here, they're huge. They're getting bigger all the time. So that's why the R is in there, because that gives you the dimension of that. So your delta A is going to be R sub I, delta A sub I, R sub I, delta R sub I, delta theta sub I. And it's all right to do it this way. I think of it in terms of R d theta and dr, but it doesn't matter. Where delta R, change of R sub I, is R2 minus R1. In that picture, it would be R17 minus R14, having a 16, okay? And the delta theta would be theta 7 minus theta 6, or whatever, two consecutive ones. This implies that the volume of the solid of height, where your solid is up here over that, is going to be the height of that depending on where you are in your X and your Y. Okay? It's a shame to go back to basically X, Y, but that's what we're doing. Above R is approximately, and again, this is alpha is a function of X and Y, R1 theta, cosine theta I, R I sine theta I. This is the Y value, that's the X value. And then your D theta, the A is going to be Ri, delta Ri, delta theta I. Okay? So once you do the region, the integral over that region, then this theta of X, Y, why didn't they put R theta? I don't know. They keep insisting on doing X, Y. You just put in your summation of all your i's here of alpha of R sub I I equal 1 to n. Now again, remember, let's use this one. If these are your thing, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. However you want to number these, they're not numbered this way or this way, anything special. They're just a counter. You know, which one you've got up to n, however large your n is, okay? And that would be the summation of I to n. You have a total of n of those, wherever they are, of f of, this is your x, that's your y, r dr d theta. Okay? Sum on the right can be interpreted as a Riemann sum for f of x, y. Why in the world do they just have an r there? Oh, I see. A Riemann sum for x, y, r. And then your Riemann sum counts the two d's together. Okay. The region R corresponds to a horizontally simple region in S in the r theta plane as shown here. Okay. Now this is truly bizarre. I've never seen them draw R in this direction and theta in that direction. I've never seen that before. What they do is translating that polar coordinate and making it look like a rectangular coordinate when they're not rectangles, but they're showing it as such. I've never seen a book do it this way. And these are your angles here, and these are your lengths here, and here is R as a G1 of theta, G2 of theta. Rather bizarre. But this is then just describing why they say dr d theta, why they separated those out in a Riemann sum. Don't sweat this. You never go back to this again, I don't think. Polar sectors R sub I correspond to rectangles S sub I. They have this so backwards. If I were naming this a sector, I'd call that S sub I and the rectangle is R sub I, but they're doing it backwards. And the area delta A sub I of S sub I, which is the rectangle, is R d theta. To me, that should be a sector. So the right-hand side of the equation corresponds to the double integral over that rectangle S. This is so strange. Of f of R, and again they're doing x, y here, r dA, where dA now represents that rectangular representation of r and theta, which is such a bizarre way to do it. From this you can write the summation over the rectangular, and calling this now a polar sector, f of x, y dA is the double integral over the rectangular sector here, f of r cosine theta, r sine theta. See, these are exactly the same f, same everything, but then r times your dA here, which was r dr d theta, r dr d theta. This is now r times dr d theta. Rather strange. Okay, and this is going from these limits were as limits to functions of theta, then you do the r first and the theta last. And the theta is going from alpha to beta, because that's what we're going from. This is going from G1 to G2. And you evaluate this from these regions, r dr d theta. Okay. This is the strangest way of presenting this I think I've ever seen. This is just the following theorem, 14.3. Let R be a plane region consisting of all points x, y, which are the same as r cosine theta, r sine theta, satisfying the condition that 0 is less than or equal to theta, g of theta I which is less than r, which is less than g of theta, g2 of theta, g1 of theta, so g1 of theta, which is less than r, which is less than g2 of theta. In other words, both of these g's are positive, and the r is in between the two g's. And the theta is in between alpha and beta, where beta is always greater than alpha, so beta minus alpha is always greater than or equal to 0, but less than 2 pi. Okay, so you're staying within 1. You're not going around and around and around. G1 and G2 are continuous on alpha and beta, and alpha is continuous on your rectangular region, or whatever region that is, R. Then this gives you your, again, y in the world is sticking with xy here. The function is function of r cosine theta, r sine theta, r d theta. And that is all set up well. Why didn't they just say function of r and theta? I don't know. Okay. The region R is restricted to two basic types, R simple region and theta simple region. So that's why I don't know why in the world they started calling them horizontally simple and vertically simple. Not necessary. Okay? Now, for R simple regions, okay, this one, you do for any delta theta, your R is always going between a G of theta here and a G of theta there. G1 of theta and G2 of theta. Okay? That's a R simple region. Theta simple region means that you're going between an H1 of R and an H2 of R. Here's H1, here's H2. That's some function of R. So your functions are this way, and your thetas are going, your R's are going this way. Here's your thetas going here. So they call this an R simple region. And your thetas are going from here to here, so you call that a theta simple region. R's are going from that one to that one. So any delta theta, theta is going from here to here, any given R. Okay? Whatever R you want. Now, let R be the angular region lying in between the two circles, x squared plus y squared is equal to 1, and x squared plus y squared is equal to 5. Okay, how are we doing on time? Got a little bit of time left. Okay, now your R here is 1, and the R here is square root of 5. Don't think it's 5, it's square root of 5. So evaluate the integral. Of the double integral over this region, okay, this region R, of x squared plus y dA. Okay? Now, again, this is one bizarre way of presenting the problem. If I were doing polar coordinates, I'd want that in terms of polar coordinates, but they're not doing that. So this would be integral. Let's get the thing here. X squared is, remember what x is? R squared cosine theta squared, because x is r cosine theta, plus r sine theta. Y is r sine theta. Okay? Say theta and write a y. I don't know what's going on. Okay? And then your dA here, in terms of r and theta, is r dr d theta. Now, if you write them that way, and I'm not suggesting that you do, but it says an angular region between two circles, two complete circles here, your r is going to be first, so that's going to be between, it's between 1 and square root of 5, because that's what the r is, not r squared. 1 and root 5, and your theta is going from 0 to 2 pi. If it's a complete circle, the radius is 0. So evaluate the integral there. That would be the integral in terms of this. Now that may look bizarre, but let's first thing we do is do it this way. Integral from 0 to 2 pi, integral from 1 to root 5. Now let's combine these things. That would be a r cubed cosine squared theta plus r squared sine theta dr d theta. Okay, because you just combined that r with the other two. Because the dA is that whole thing there. Okay, I probably should have put parentheses to begin with. And you might put them again here. Okay. Now, which one are we doing first? And it really didn't matter. I hope it doesn't matter. Let's do the dRs first. So when you're integrating with respect to r, you treat the thetas as if they're constant. Okay? So what would this give you? Integral from 0 to 2 pi of, integrate that with respect to r. R to the fourth over 4 cosine squared theta, just treat that as a constant, plus r cubed over 3 times the sine of theta. Just treat that as a constant and evaluate that between r equal 1 and r equal root 5. Okay? And then we'll do our d theta later. Okay? So let's evaluate. That'll be integral from 0 to 2 pi. We'll come up to that later. We're going to plug in these values here. Well, if r is root 5 and you're raising that to the fourth power, that would be r squared would be 5. So r to the fourth is 5 times 5. So that would be 25 fourths cosine squared theta plus, now this will be a bit more bizarre, that would be, say that again? 5 root 5 over 3. Because if this is to the third power, that's root 5 times root 5 is 5 times another root 5 is 5 root 5 over 3 times the sine of theta. And then you integrate with respect to theta. Okay. This is not a very pretty sight because the cosine squared, you're going to have to go through and do a, let me get on the right page here. Use a double angle formula to deal with that. And we don't have enough time left today to go back and retrieve those double angle formulas. Okay? I'll just write it down, but you can go back and get it for yourself. Let me give you a hint of where they come from. If you remember, sine of 2, let me use theta, is equal to 2 sine theta cosine theta. We don't need that one. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. I don't know if you remember those, do you? Sine squared theta. Okay. Now, what's that? I don't understand. Okay, yeah. Yeah, we're not doing that integral yet. We're trying to do this. I'm trying to tell you how you get this to a double angle formula. Okay? And you don't need the sine 2 theta in this problem, so I'm going to erase that completely. okay? But we will need the cosine 2 theta. Okay. I don't know why my eraser wouldn't come up. Erase that and that. Both of them are pretty ugly. Sine squared theta. Okay. Now here's the other thing we need. The Pythagorean identity that tells us that 1 is equal to cosine squared theta plus sine squared theta. Now, we want to get cosine 2 theta, so let's add these two together. 1 plus cosine 2 theta is equal to 2 cosine squared theta plus 0. Right? All right. Now, here we have a cosine squared theta, and here we know that cosine squared theta is equal to 1/2 plus cosine 2 theta over 2. You don't have to write it that way, but I just chose to. Okay? So, you could change this integral to be, and this is what they're doing there, the integral from 0 to 2 pi. Okay? I'm going to pull the 25 over 2 out from this one. And that leaves me a 2 cosine squared theta in there, which then I'm going to leave as 1 plus cosine 2 theta. I wish I hadn't done it yet. Just going to leave the 2. No, I did that wrong. This should be an 8 here. That leaves me a 25 over 8, and 2 cosine squared theta, would be 1 plus cosine 2 theta. Okay? And I'm going to put my d theta here, and then do another one, plus 5 root 5 over 3 times the integral from 0 to 2 pi of sine theta d theta. Okay. Now, this is integrable, that's integrable. Okay? Do we have time to do them? Maybe. Let's see if we can. The integral of 1 would just be 25/8, and that would be, put that on the outside, theta plus the antiderivative of cosine 2 theta would be sine 2 theta over 2, right? Okay. Plus, and let's go 0 to 2 pi on that one, 5 root 5 over 3, and what's the antiderivative of sine theta? Minus, right, cosine theta. And we'll evaluate that from 0 to 2 pi. Okay. Now, plugging in, we get 25/8 times 2 pi. So that will be a 4 down here and a pi up here. So 25 pi fourths. Plus, okay. Now the good news here, sine of 4 pi is 0, right? So that doesn't contribute anything. So this is 25, what they'll wind up with, fourths pi, 25 pi over 4, okay? And over here we have a plus 5 root 5 over 3 times, and what's cosine of 2 pi is? That's going to be a 1, but it's a minus. Minus a minus would be plus 1, and those go to 0. So I think our answer is 25 pi over 4. And I can't even find the problem we're on. No, close but not quite is 24 pi over 4. And I must have dropped, I'm not sure where I got my 25. Oh yeah, I do know where that is. So I dropped a thing somewhere, but that was example 2. Now, we're out of time, and frankly, I think that's enough polar coordinates for right now. So homework exercises, do either 5 or 7. They're both at Calc Chat. 5's at Calc View. Do any of the odds, 9 through 15. They're all at Calc Chat. 9's at Calc View. And then try to do any of the odds, 17 to 25. They're all at Calc Chat. 17's at Calc View. And don't mess with going the other way. Okay? We will, well, actually, those are pretty easy, actually. Oh, they're also converting. So any, do 27. It's also at Calc Chat. Now let's just stop there and move on to center of mass and moments of inertia. And we will pick up there in 14.4 next time. Okay. Key here, we're going to try to finish that one pretty quickly, then do surface area, hopefully fairly quickly. I want to get the triple integrals. That's the most important thing, I think, of what we have left is triple integrals. That's a fairly long section, so I want to get there. And we may not get to triple integrals in other coordinates, because that's going to be pretty hard, and I doubt if we'll get the Jacobians. Okay, so anyway, we'll try to do that to wrap up the term. And your last test will be chapter 14 test only. Okay? All right, good deal. All right, we'll end it there.